Okay, this is hour 2 for Physics 1C. Now we're going to start talking about an application of what we learned last time, or what we learned in the last video. So we're going to talk about motors. In particular, we're going to be talking about what's called a DC motor. A motor that operates off of DC, which is direct current. Okay? And all the principles that we need for this come from what we just learned about. And I'll write down what they were. We said that if I have a loop of wire, and it's placed into a magnetic field, that the wire has this thing called a magnetic moment, and that the torque that's on the wire is given by this expression, the magnetic moment cross product with the magnetic field. What does that mean? Well, if we look at this picture down here, let's just look at the little red and blue wires. Don't worry about anything else right now. In this picture, we have a current that comes from the positive side of this, so it flows up through the red wire and then through the blue wire and back to here. That allows us to have, effectively, a loop right here. What I want you to do is I want you to verify for yourself that if you take your fingers of your right hand and you rotate the fingers of your right hand in the plane of the loop as if you were basically sweeping the current along, so imagine you're pushing the current along, what direction does your thumb point? Does it point down or does it point up? So rotate the fingers of your right hand as if they were pushing that current around. What direction does your thumb point? Down. Your right hand, Mr. Miars. Sweep the current along, and your thumb should be pointing downwards relative to the screen. That is the direction of the magnetic moment of the wire. Yeah, sweeping, like, the wire is like this, right? So it's like, let's make this a little simpler. So say this is the front, this is the back. The current goes like this. So we have a wire that's oriented basically so that the circle is kind of perpendicular to the board. Does this help you to see it, Mr. Miars? If you swing your fingers like this, you get your thumb points this way. And that's the direction of the magnetic moment. Okay. Can most of you see that you get your thumb pointing down if you do that? Okay. Now, because your thumb points downwards, what direction should the loop rotate? Magnetic moment points down. What is the loop going to tend to do? Is it going to rotate counterclockwise or clockwise? What direction does that orange vector want to point? The orange vector is going to tend to rotate until it becomes parallel with B, right? Is it going to rotate clockwise or counterclockwise? Oh, and the magnetic field now, I left this part out. There's these magnets here, and it goes from north to south, so it's counterclockwise, yeah. Counterclockwise. You guys got it? So in this scenario, with current flowing this way, it's going to tend to rotate so that the magnetic field, the magnetic moment is going to rotate till it aligns with the B field. Okay? So it's going to tend to rotate like that. All right, so now let's make this picture bigger. Do we understand how do we get from picture A to picture B? Does anyone have any questions? Do you understand how to get from picture A to picture B? Current flows, the loop is going to tend to rotate until it's aligned like this. So the blue side comes up and the red side goes down. All right. Now, the problem with what we just described is that when you get to this position, normally the torque would be 0, right? The torque would be 0 normally. And so the loop would not continue to rotate. But what is a motor? What is a motor? A motor is something that when you pass electric current into it, it rotates. You could have a motor inside of a fan. That's a really simple type of motor, where you plug the fan into the wall and the fan starts to rotate. That's an example of a motor. At its core, it's something like this that's going on. But how do you make it rotate continuously? So that's what this little brush here and this commutator do. And I'm going to show you a video of this, so if you don't fully understand it from the pictures, just bear with me. So in the first picture, current flows into the red side of the rotor and out the blue side, on this side. Therefore, the magnetic torque causes the rotor to spin counterclockwise, like this. You'll notice that there's like a split here, and there's a split here. So, and that those splits are exactly 90 degrees apart from these contacts. And these contacts are not like normal, like just fixed contacts, but they're brushes that connect, so it's like a wire brush that touches this, okay? So when you get to this 90-degree point right here, you have an opening in your circuit. And that opening makes it so that there's no longer current flowing in your wire. As said here, there's no current. Does that make sense? Hopefully you can see from this picture here that when you get to this point, when it rotates 90 degrees, you're not going to have any current flowing through your wire. So what's that going to make it do? There's no longer a torque acting on the wire. But if you think about it, this loop has basically just rotated from this position up to here. So certainly by the time it gets to this point... what? What do you guys say? Something happen? That's right, Meowers. The momentum will carry it over. Exactly. Does that make sense? There's no force on it anymore, so it doesn't want to stay in this orientation. There's no magnetic moment anymore, because there's no current. And just to remind you, the magnetic moment, mu, is equal to number of turns times I times A. So if the current drops to 0, you've got no moment. So yeah, so momentum will just carry it past. So what happens then? Well, what happens is that the side that was originally the red side is now the blue side, right? But look what's happened. Before, the current in the blue side was going this way, and now the current in the blue side is going this way. And why does that happen? Because of these brushes and because of this ring. As soon as it goes through a quarter of a cycle of 90 degrees, the current reverses. And now the current will continue in this position until it rotates around another 90 degrees, and then the current will switch again, and it'll make it so that it keeps rotating. Yep, the brushes are... This is like an electrical contact. It's an electrical contact, yeah. And that's basically how a motor works. And if we were at the school, I would show you a motor, and I'd pass it around, and I'd show you guys that it's really simple, and, you know, that's what it is. But this is a pretty decent representation of it. So, yeah. Yeah, and so this motor would basically continue to rotate. Although, it wouldn't rotate smoothly. So this wouldn't be a good motor. This is a good motor for describing how things work. It's not a good motor for, like, producing a commercial application, okay? So we're going to watch a video because I think that all the things that we just discussed are really hard to visualize. But this video does a pretty good job of it. So it's about 5 minutes long. Probably, it goes into some things that we don't really need to talk about, but I think you'll find them interesting. I hope so. So I'll change windows. We're going to look at this and see if it helps to teach you how a motor works. Y'all can hear that, right? Just making sure. It was only on for a second. I'll play it again. Yes? No? You can hear it? Okay. Start it over. I think I have the closed captions are on. Do I need to turn the volume up, or is that already loud enough? It was good? Okay, we'll just leave it like right about half. Okay.
I'm just going to stop for a second. Do you know what he means by load? That's a phrase we haven't started using in this class yet, but we will. What does he mean by load? So it would be like, what are you going to do with this motor? Like, is it just going to rotate, or is it going to power something? Is it going to power a toy car? If it powers a toy car, the load would be the need of the wheels to actually, like, push the car, right? So imagine if the electric car that you're trying to drive around is really, like, low in weight. In that case, it's going to have low load. But if it's a really heavy car, it's going to be like a big load in a way. Just like, imagine, like, filling a truck up with a big load of, logs and cement and some things that are heavy or something like that. It would increase the load on the thing. It's related to work, yeah. What's another example? So maybe you're using the electric motor to rotate the blades of a fan. That's probably not a big load. It doesn't require a lot of work to get the fan blades rotating, right? But what if instead you were using this motor to, like a winch to, like, pull, like a truck that's stuck in the mud or something like that, and you attach a rope and you put it on this motor and you're trying to pull this thing out? Well, that would be like a heavy load. Does that make any sense? I don't think I explained that very well. The idea is that the reality of these motors is, like, you have to connect it to something to do work for you, and that thing might require very little work, or it might require a lot, and that's the load. So what he's saying is that one type it starts up with a lot of torque, but then as soon as you put a load onto it, it kind of, like, slows down. You may have experienced this, maybe, with motors you've used. Like, I don't know, like a power drill. If any of you have ever used, like, a power drill to, like, screw things into the wall, do you guys know what I'm talking about, some of you? It's like you get a screw, it stalls out. Yeah, okay, you guys know exactly what I'm talking about. That's good. Okay. So that's like you're putting a heavy load on it, right? At first, when you're screwing a screw into the wall, the load's not very high, but then when the screw gets kind of all the way in, it's not gonna, it's a little harder to, so harder to turn, which is a big load. So we'll keep going. Okay, this is really important. We will talk more about the theory in a few weeks, but I'm going to let him finish because this is a really important concept of back EMF, and it's really complicated. So. So, like, you don't want the motor to run too fast, or it can, like, cause problems. So you have to have a load. You need to have some load on it, or else it will cause problems. That's kind of what he's saying. He says, is this why they use capacitors to store charge? Capacitors can be used to help some of this process out, yes. To kind of smooth out some of these things. All right, I'm going to let him keep going. But we will talk about back EMF. We're also going to talk about induction. The idea is that you don't get anything for free in this universe, so when the loop rotates, and it rotates inside of a magnetic field, it turns out that actually causes electric current opposite to the direction that you want. And it's just how things work. Okay, was that video helpful to y'all? That helped to understand what's going on? I know he went into, like, a lot more detail, but it was really just this opening part here that I wanted you to see. Okay, good. Okay, so I thought that video was really good. I watched, like, 6 videos on motors before class, and this was the one that I thought was the best. There could be other ones out there, too. I just, some of them were really long. This is 10 minutes long. I didn't look at those. I just looked at the ones that were 5 minutes or less. So, okay, so you have some understanding of what a motor is. A motor, again, is a device that takes electricity and it turns it into mechanical energy. At the end of the day, that's what it is, right? I'm going to write that down because I think that's relevant, just so you can remember this, that basically what a DC motor does is the motor basically takes in electricity and then it outputs mechanical energy. In the form of rotational motion, usually. Oh, shoot. Yeah, I gotta switch things. Are there hotkeys to do that kind of stuff? I don't know. Anyway, okay, so what I was trying to say is that electricity comes into a motor. What the motor does is it basically turns it into mechanical energy. It doesn't work to just Alt-Tab Ash because the audio from the YouTube videos doesn't get picked up whenever I'm just screen sharing. It only gets picked up when I'm window sharing. Okay. So otherwise, I guess it's just picking up the audio from my mic, and that's it probably. And maybe that's setting something I could change. Maybe I should look into that. Okay, so again, a motor is a device that pulls in electricity and outputs mechanical energy in the form of rotation. Very powerful if you think about it, right? All you need is electricity, like a battery, and you can make something move. This is something we all learn about as kids, right? If you have any kind of toy that has a motor in it, of which there's lots of them. It could be like a toy car, it could be a little toy fan, I don't know, but yeah, you plug a battery in and it gives you rotation. It doesn't work forever because eventually the battery goes dead, right? But it's a pretty powerful concept. Okay. So you asked a question. Does anyone have any questions before I keep going? Jesus is typing. I'm going to let him type, and I'm going to answer one of Meower's questions. Mr. Meowers, you had asked, are we going to learn about generators? And I will say that when we look at generators, they look exactly like this. 100%. Because a generator is a motor operating in reverse, basically. One that basically goes mechanical energy into electricity. That's what a generator is. And it literally works by, instead of the force doing the rotating, you're doing the rotating. You basically rotate a wire inside of a magnetic field and it generates electricity. Where can you find the diagram? This diagram is in your textbook. It's in chapter 27. Yeah. And then other books have other diagrams if you want to look them up. I think this one's pretty good, honestly. It does a pretty good job of kind of showing you what's going on. It shows you the brushes and the commutators and all this kind of stuff. What I liked particularly about that video is how he basically said that this is just a too simple version. It wouldn't work very well. But then by just adding a whole bunch of extra armatures, this thing was called an armature, you can smooth it out, which is pretty cool. All right, let's keep going because we still have a lot of stuff to talk about today. Savart law. Is that what we're on now? Okay. All right. So this next portion, we're now moving into the next chapter. I think it's chapter 28. And this chapter is called Sources of Magnetic Fields. So we already know about a few sources of the magnetic field. We know about magnets. We know about the Earth has a magnetic field, right? That's all we really have so far. We also know of something that I mentioned early on, which is that current-carrying wires also produce magnetic fields. And pretty much that's what this chapter is about how little wires that carry current produce magnetic fields, and we want to understand kind of how that happens, okay? How does an electrical wire produce a magnetic field? And how big is it? What are some shapes that can produce specific magnetic fields? We're going to look at the magnetic field that's created by a line of wire. We're going to look at the magnetic field that's created by a loop of wire. And then we're going to look at the magnetic field that's created by a bunch of loops of wire. Okay, so these are the type of arrangements that carry current, and all of them are going to produce magnetic fields, and we want to understand all of those. We're going to start off with the simplest one, which is this one, and then we'll talk about this one, and then we'll talk about this one. And by the end of the class, hopefully you have some understanding of, given a current-carrying wire, what type of magnetic field does it produce. Now, in order to do this, we're going to have to use another empirical equation. If you remember when we first started talking about magnetic force in the last chapter, we just talked about the magnetic force and described that it was given by this QV cross V equation, okay, the Lorentz force.
And I told you that we can't really derive that force, and we have to just kind of accept it. Well, what I'm about to tell you is also something that I can't derive. This is an empirically observed law. It's called the Biot-Savart law. I might not be pronouncing that right, but I know you don't pronounce the T's. It's like Biot-Savart or something like that. Law. Okay. The Biot-Savart law works like this. This is... I'm just going to warn you guys. It's pretty tricky. Suppose that I have a wire. Okay, so I have a wire. And say that this wire carries some current. Let's say it goes this way. And this wire is kind of in the plane of the page, okay? It's just a piece of wire. It could be a piece of wire just lying on a table or something like that, but it has current flowing through it. Flowing this way. And what the Biot-Savart law does is it says, suppose that I come to some point... Where's a good point to do this on this picture? Probably here. Suppose that I come to some point here that I call P. And let's say that I want to ask the question, I tell you that the wire produces a magnetic field, and I want to know what the direction and the strength of the magnetic field that's produced at this location is. That's what the Biot-Savart law does. It says, what is the magnetic field at point P? That's the question that it answers. Okay? And what the Biot-Savart law says that we need to do is it says you need to look at your conductor, your wire, and you need to break it up into little pieces. So say we break off a piece right here. Piece of our conductor. And then say, okay, that little piece of wire has a current element, and I'm going to say that there's a vector associated with it that I'm going to call dl, and it's going to point in the same direction as the current. Very consistent with what we did at the beginning of class with that problem with the semicircular wire. So there's this little piece, and this little piece is going to produce a magnetic field, and of course it's going to be a differential magnetic field. And the size of the magnetic field at point P is going to be equal to dl. We're going to need to have a cross product because it's the magnetic field after all. I'm going to do this one with an actual arrow though. So we draw an arrow from here to here, and of course it doesn't actually work because this program is awful. Okay, we go. It's not that bad, but... So we go like this, and we go like this. So that's going to be my position vector. Okay, and we're going to say this little piece of the wire produces a magnetic field that's going to be given by dl crossed with r. Has to be crossed because it's magnetic, right? All the magnetic stuff we've done always has a cross product in it, right? But it's not exactly crossed with r. It's actually going to be crossed with r hat. And then we're going to divide it by r squared. So we got our 1 over r squared in here. Wait, is it r squared? I think it's r squared. Okay, I gotta cheat because this is something that I don't necessarily remember. Okay. Apologize. It is r squared. Okay, all right, I remember correctly. So it's equal to dl cross r hat over r squared. But then there's also some other things. You have to multiply by mu naught, which I'll tell you what that is. You have to multiply by I, and you have to divide by 4 pi. So you get this 4 pi r squared that shows up here. That's, what is required? The question is, what is required to prove this that we lack? Maybe I'm wrong, but I don't think you can prove this. I think this is just what we have, Ash. It's just, we can't derive this from first principles. I'll go look, I can go look at my graduate textbooks, and maybe you can go look on the internet. You can see if, you guys go do it right now, like,
See if there's a derivation of the Biot-Savart law. Yeah, it's observation. It's empirical. It's empirical, yeah. Just like the other one. This was also empirical. That was an empirical law, too. We didn't derive it, right? So, this is the same thing. There we go, though. That's the Biot-Savart law. Doesn't it look awful? Doesn't it just look completely and totally... How am I supposed to understand this? Well, there's a few things we can take away from this. First of all, what's the direction? That part we can figure out. So it says we need to do dl cross r hat. Okay, well, what's r hat? Well, r hat is the vector that points in the same direction as r, but it's a unit vector, right? So really, if we do r cross dl, we're going to get the direction of our magnetic field. What direction is it going to point? At point P, what's the direction of r cross dl? Keeping in mind that the wire is in the plane of the board, so dl is in the plane of the board. R is in the plane of the board. So dl cross r has to either be into the page or out of the page. dl cross r, what does it do? You got to go point your fingers in the direction of dl, right hand, and then rotate your fingers toward r. Ow, okay. I think you guys are starting to get this because I'm getting much more answers. Before, like, only one or two of you were answering. Now there's like 4 people answering, so I hope that you all are getting a little close to this. Yeah. At this location, the magnetic field points out of the board. We'll use a different color. That's our dB. That's the direction of the magnetic field over there. What would it be on the other side? Suppose we came down here, and I look at another point on this side that would be, like, let's say, P prime, and I draw another vector for R. It just makes me so sad that I can't just... Yeah, whatever. So we do an R prime. How about over here? What direction does it point on this side? Okay, again, you go to DL across R. It's in, right? Okay, so now we're learning things. This is something that we can actually use. It looks like that if I have a wire that goes this way, the magnetic field on this side, you can test it out. You will always get the same direction. All along this side over here, it looks like the magnetic field is coming out of the board. And all along this side, it looks like the magnetic field is going into the board. Can you see that? Doesn't matter what point I pick over here. I'm always going to... DL cross R will always work the same way. So magnetic field over here goes this way. Magnetic field over here goes this way. Now that's useful. All right. Now, how could we memorize this? How could we memorize this? Well, suppose you take your thumb and you grip the wire. Imagine that you're holding the wire like you would hold a pencil with your right hand. But you point your thumb along the direction that the current is flowing. Can you see that the direction that your fingers rotate above the wire would be out of the page, and below the wire would be into the page? And it hurts your hand a lot once you curl it around about 90 degrees, but did that make sense? You grip the wire, so take your right hand and imagine you're gripping this wire, and you're pointing your thumb along the direction of the current, okay? And then look at the way that your fingers rotate. They rotate in a circle around the wire, right? Can you all see that? Okay, maybe you can't. It's okay if not. So let's look at it from a different perspective. You can see it, that's good. What if I told you that we have current, so I have a wire, but now let's say, just for simplicity's sake, that this wire, okay, is pointing with current that flows into the board, okay? So I've got a current that flows this way. Got a current that flows this way, right? Take your thumb, point it into the board, okay? And then swing your fingers around in a circle. What direction would they go? Clockwise or counterclockwise? If you put your thumb in the board in the direction of the current, so again, we're imagining a long wire comes out from behind you into the board, clockwise, right? And that's exactly what the magnetic field would do. Over here, the magnetic field would point this way. Over here, the magnetic field would point this way. Up here, this way. Down here, this way. And if we were to place little compass needles around a wire, this is exactly what would happen. I'm going to show you in a second. But basically what happens is you get a magnetic field that's circular. Circular magnetic fields. I think that's pretty cool. If I have a wire that carries current, it produces a magnetic field lines that are circular. I believe it's impossible to produce electric field lines that look like this, at least according to the methods that we've learned before. Something that we'll talk about later on. Do you want to see the video to prove to you this actually works? Do we want to listen to the audio? We probably do. Let's listen to the audio. Oh, I'm sorry. That's times 2 speed. All right. Did you want to predict what direction are so right now they're pointing north, okay? They're all pointing north because of the Earth's magnetic field. This one's just stuck or something like this. He's telling you that the current is going to flow up, right? So point your thumb along the direction of the current. What direction do you think the needles are going to point? You think counterclockwise? Okay. Let's see. You guys got it right. So the field's bigger the closer you are. That should make sense. So I think that's really neat. So what he's showing here is like when you get a little farther away, it's now not just the field of the wire that shows up, but it's a vector combination of the field of the wire and the field of the Earth, right? So then it's going to point kind of in a diagonal direction. Does that make sense? Does that field spiral out? No, it doesn't really spiral. It's like rings. It's just like rings of weaker and weaker fields. I think that's all we want to see from this video. What else is he going to do here? He's just going to talk a bunch. Okay. So, there we go. Magnetic field of a current carrying wire. Okay. So, wires that carry current, they produce circular fields. So basically, Nathan, if you go out to a farther distance, what this equation tells us is that the field gets weaker, basically, right? The size of the field is proportional to 1 over r squared. So as the farther away you get, we're not on the picture anymore. Thank you. I'll switch. My bad. Okay. So sorry. Yeah. So, yeah, Nathan, to answer your question, we get these circular magnetic field lines the farther away we get. So if we come out to some distance really far out here, then according to this equation, the magnetic field gets weaker. You're right, Nathan, that the Earth's magnetic field has more influence the farther you are away from the wire, because it looks like the size of the magnetic field is going to fall off as r squared. Or something like that. Something like r squared. We'll see how that works out. Okay. What is this thing?
So, this tells us the magnetic field, by the way, just of one little segment, just so we're clear. If I want to find the magnetic field of the wire itself, I would then need to integrate over the entire thing, and we'll do some of that. But let's say something about this mu naught thing. So, mu naught, you can probably guess, is kind of similar to epsilon naught. It is a very interesting constant. It's a constant, and it happens to be exactly equal to 4 pi times 10 to the negative 7. And then you can figure the unit out from here if you really want to. This is units of 1 over r. So it's going to be, I think it's Teslas times meters divided by amps. You can work that out for yourself from this equation, but the unit of mu naught has to be proportional to Tesla from that, divide the amps to the bottom, multiply this r to the left-hand side, and then dl has units of meters, so Tesla meter over amp. So this is, I think this is called the magnetic, it has a really nice name, permeability of free space. It's kind of a nice name. Okay. Does anyone have any questions? And again, understand that I will do an application of this. This shows up in EM. What's EM? Electricity and magnetism? Electromagnetism. I'm assuming you meant optics.
Electromagnetic field. Wait, what do you... What's an electromagnetic field? We've talked about electric fields and we've talked about magnetic fields. What's an electromagnetic field? Are you talking about the electric and magnetic fields of a beam of light? Is that what you're talking about? Okay, I'll just move on. So, the, yeah, so let's do this problem. Okay, we're going to do a problem where we actually use this. We're going to do 2, I believe. Only 2 that we use this. And I do not believe I gave you any homework problems or lab manual problems where you have to use this, okay? So don't worry about this equation, except for to understand the derivations we're going to do, because it's going to be the results that you care about, okay? The results of these derivations that you care about. So the first thing that we're going to do is we're going to look at a long straight wire. I will probably just start drawing it and talking about it, and then we will continue after we get back from break. So we're going to start off with the long wire. It's going to carry current. So this is going to be our wire. We're going to say that it carries current, and and we're gonna chop it off at the ends too. So it's going to be a fixed length, and this wire is going to carry current in this direction here. We're going to situate it inside of a coordinate system. Something like that looks like right about the middle there. So we're going to have a coordinate system right here. Because it's like not a physical piece, we're just going to kind of create this into a dashed line. So we've got, this is going to be our x direction. And we're going to be finding the magnetic field at this location right here. We'll call that point P, I guess. This is going to be kind of similar to a derivation we did in the first chapter. So we're going to say that this wire carries current like this. And we're going to say that
the length of the wire is going to be 2a. So this point right here is going to be y equal to negative a, and this point up here is going to be y equal to positive a. So that's y equal to 0, that's the origin, and then our x direction's off this way. Okay, and we're going to use the Biot-Savart law. The Biot-Savart law, it said that we need to do this thing. I didn't select everything. So this is the equation we want to apply. And this requires that we take our wire and we break it up into tiny little pieces that we call DL. So we'll do that. We're going to start off by taking a piece like right here. That's going to be our DL. It's going to carry a small amount of current. And the direction of DL is going to point from there up to there. So we'll just call it, where is the right way to, let's draw it right here. So that's going to be DL. That's an infinitesimal piece of the wire, basically. And we need to have a position vector. Our position vector is always drawn from the current element. Oh, really? I thought I had it that way. This way, this way. It's always drawn like this. You go from the current element out to the point P. That's a position vector, so we're going to label it as R. This side is going to be X. And then this side, baby, obviously, is going to be Y. And it's a right triangle. Let's define the angle between DL and R. And of course, there's also going to be an R hat vector on here. I'll draw it a little bit bigger than normal. So that's going to be R hat right there. R hat is a unit vector that points in the same direction as R. We're also going to need the angle here, phi. I think that's everything we need. Okay. So, according to this equation, the direction of the magnetic fields is DL cross R hat. What direction is that going to point at point P? So look at DL cross R hat. Go from right fingers of your right hand, point towards DL, rotate to R. What direction is your thumb point? So take the fingers of your right hand, point them straight up on the screen, parallel to that wire, and then rotate your fingers towards R. And here's the other thing. You have to rotate through the smallest angle. So you need to rotate basically from here to here. Rotate your fingers of your hand just like that, right? So point your fingers up along DL, and then rotate, swing them down to R. You guys get in? In, right? Okay, good. It's in. So here's the weird thing. You put it right here. So the magnetic field, what we're calling dB, points in. You'll have to convince yourself that no matter what position I picked on here, the magnetic field would always point inwards. That's kind of nice. We don't need to do any trig, at least to represent this. It always goes into the board, no matter what piece of the rod we picked. Okay. Okay. So there's our DL, there's our R, there's our phi. Okay. All right. So there we go. So let's start to kind of unpack what this says right here. So this says that the magnetic field dB is given by, okay, mu naught, it's given by I, the current. We divide by 4 pi, all those things, those are fine. DL cross R hat. What is that going to be? It's going to be equal to DL multiplied by the magnitude of R hat, which is 1, and then multiplied by the sine of the angle between the two of them, which in this case is the sine of phi. Yeah. R hat sine phi. And then we divide that by r squared. But on our picture,
the magnitude of dl, I believe, is just y, right? It's like dy, because it's in the y direction. So I think what we want to do is we want to change this to dy now. Because after all, the dl direction is the dy direction, right? So we're in the y direction here. Positive y this way, negative y that way. I think we're done. I think we can actually do this integral as long as we replace r with something related to y here. So, oh, the phi as well, right? We need to deal with... Yeah. So if you want to try that yourself, you can. We're going to take a break until 8:20. And we'll come back and we'll finish this up. Give you some time to kind of think about what we've drawn here. And think about solving it yourself if you want to. Okay? Any questions? Yeah. Yeah. The r hat just becomes 1. Yeah. This will just be 1. Okay, let me pause the recording.